And
Okay,
please.
Okay, so thank you for invitation to speak on this seminar. So I apologize, my talk is not really related to reaction kinetics, but it just will be about normal forms theory. It's quite pure mathematics, but I think this method and some ideas can be also useful for reaction kinetics, for studies in reaction kinetics. So the talk is based on two recent works. One is with Tatiana Petek on computation of Poincaré-Dulac normal forms, which just published recently in the Journal of Differential Equations. And another work is work in progress with Sebastian Walcher. But we have already first version in archive, but we now almost finished the new version that we hope to put in archive soon, maybe in 1 or 2 weeks. Okay. So first I recall some main notions of Poincaré-Dulac normal form theory. So assume we have a system of differential equations, system 1, so it's our main system, x dot equals f of x. F of x, so it's a vector field of system of differential equations. I use the same word, system of differential equations, or vector field. So we can expand fx in power series. So a of a times x is a linear part, and then we have a nonlinear part where fj is n-dimensional vector-valued polynomial, homogeneous polynomial of degree j. So this sum is the sum of vector homogeneous polynomials. Lambda 1, lambda n, so are now eigenvalues of matrix A. We mainly will assume that A is diagonal matrix. N0 is natural numbers and 0. So this is N0. And alpha usually will be vector from this N0, or sometimes is from Z to N. Sometimes alpha also will have negative coordinates. So lambda alpha is just inner product or scalar product, so it's defined in this way. And alpha, absolute value of alpha is just the sum of all alpha 1, alpha n. By x to the alpha, we denote such monomial x1, alpha 1, x2, alpha 2, and so on. So x here is a column vector, and x to the alpha monomial. And Poincaré, we can...
Excuse me, Valery. I don't see x to alpha here in this page. What is the rule of x to alpha? This power, where I see the definition, but where do we apply it? Where do you use it?
Sorry, x. You do not see x to the alpha?
Yes, I see only the definition.
Yeah.
But I don't see where do you use it.
Yeah. It's here, for example, in f. F is polynomial, yeah? F of x.
Yes.
So f of x is polynomial. So terms of polynomials are some coefficient times x to the alpha. Yeah.
Okay, so fjx is a monomial so that the absolute value of alpha is j.
Absolute value. Okay, absolute value. Okay, absolute value is defined this way, just a sum of coordinates. Yeah.
Okay.
Yeah. Yeah. So now we can make a change of coordinates of the form 2. So from coordinates x, we go to coordinates y. So it's power series. It's called near identity transformation because x is y plus high order terms. And then it is easy to see that we will arrive on the system of the same shape, but instead of f, we now have g, and J will be another polynomial. So the main idea of the normal form theory to find transformation of two such that which transforms our original system to a simpler system. Yeah. So our idea, our goal is to get a simple system 3 as simple as possible. Of course, it will be the simplest if it's linear system. It means if all j are equal to 0, but it's not always possible. But we can, so x to the alpha now is in the case entry, so j is a vector, yeah, j is vector, so x to the alpha in case entry is a so-called resonant monomial if it is of such form, such a number, j to the alpha is number, uh, uh, y to the alpha is like this x to the alpha, and such that this is true, lambda alpha minus lambda k is equal to 0. And system 3 is in Poincare-Dulac normal form, or just in the normal form, if this series 3, contains only resonant terms, Or another way to define a normal form system is in the normal form is if all this j, we can consider j tilde, gj tilde as a vector field. So system 3 is in the normal form if every gjg commutes with vector field ay is equivalent definition of Poincare-Dulac normal form. But so we can look for this transformation, which transform our system in for transformation 2, which transforms our system to for form 3. And you see this is a series, but this series is not necessarily convergent. So normalizing transformation can be divergent. Here we have a definition. We say that lambda 1, lambda n are in, so it's eigenvalues of our linear part A. And we say that the spectrum, so it means that these numbers is in the Poincare domain if there exist lines through the origin such that all eigenvalues are strictly on the one side of this line. In particular, the convex whole of these numbers does not contain 0. And then we have a theorem which is due Poincare and Dulac. Consider if we have our analytic system with eigenvalues of matrix A lambda 1, lambda n. So if the spectrum is in the Poincare domain, so we also say that we will see that it means that we do not have so-called small denominators, then there exists a convergent analytic transformation to the Poincare-Dulac normal form. So it's one condition. So one condition is Poincare that this convex hull does not contain 0. Another condition is due to Ziegel. Condition of Ziegel is such: if there exists C, constant C and nu, such that for all alpha, such that absolute value alpha greater than 0, and for all k from 1 to n, we have this condition, then there exists a convergent transformation of system 1 to its normal form. So condition of Poincare and Dulac is the left-hand side is just greater or equal constant, some constancy. But here, in Ziegel, condition of Ziegel is weaker because it appears alpha to the minus nu. It can be a quite small number. Okay, and essential further step in the investigation of the convergence of normalizing transformation is due to Victor Pliss, who was my supervisor. And the condition is if for system 1, the non-zero elements among these numbers satisfy condition 4, and some formal normal form of system 1 is linear, then there exists a convergent transformation to normal form. And we say that system satisfies Ziegler-Pliss condition if the non-zero elements among this satisfy condition 4. This condition.
Excuse me, Valery.
Yeah.
I think the first condition is easy to check. Is it? The previous condition.
This condition?
No, the previous one, what we had on the previous slide.
Yeah, upon correct condition, yes.
Yes, this is simple.
Yes.
But the other one is not.
Yes, it's simple too, yeah. Yeah, the other one maybe not, but we will see that we have a very simple criteria to check this condition for. Okay, so we say that system satisfies Ziegler-Pliss condition if the non-zero elements among this satisfy condition 4. And in my opinion, among the most important contributions to the theory of ODEs in 20th century are results of Alexander Bruno on convergence of normal forms. They were published in this paper, Transaction of Moscow Mathematical Society. And he gave two famous conditions which are sufficient for convergence of normalizing transformation. So first condition is so-called Bruno's condition omega, which is properties of eigenvalues. So for first condition, we defined this number, omega L, as infimum of these numbers over all alpha, for which this is not equal to 0, and for alpha, this one, yeah? So if for this omega is holds this inequality, we say that condition omega is satisfied. And the other condition is so-called condition A, which in fact consists of three conditions, A2, A1 prime, and A2 and Y2 prime. And this is condition on the shape of the normal form. I formulate only simplified condition A, and this is this one, because these conditions are not easy to formulate. And even I formulate is not easy to understand what is going on. So, but this condition is quite simple. And we say that normal form satisfies simplified condition A if it can be written in a special form, where alpha x is in form of scalar power series, which with alpha 0 equals 0. So you see that if this function alpha is equal to 0, then identically equal to 0, then we have a linear normal form, and in fact we have this case which was studied by Pliss. Okay, and Bruno's theorem says if the analytic system x dot equals a x plus f of x satisfy conditions A and omega, then it admits a convergent transformation to normal form. And in the case of one-dimensional, actually this Bruno theorem Bruno also studied the case of germs of holomorphic diffeomorphism is more or less the same theory. And in the case of one-dimensional gems of holomorphic diffeomorphism, Yakos proved that Bruno's condition omega is also a necessary condition for convergence. So it's a famous paper. Yakos theorem de Siegel numbers the Bruno at polynomials quadratics. Petits divisors at dimension 1. And the results obtained in this article were among the reactions to award Yakos Fields Medal in 1994. But as I said, this is the simplest case which we studied of Bruno. So in my opinion, the results obtained by Bruno about convergence are much more important than this result. Okay, and I would like to try to explain the main idea of the proof of Bruno's theorem. This theorem is proved using so-called Newton's method, which was, in some cases, goes back in this context to Kolmogorov, but in my opinion, it mainly goes back to, again, to Victor Pliss. So we would like to construct transformation to the normal form, So this is normalizing transformation using iterations as follows. So let's assume that this expression coincides with the normal form up to terms of order m. Then there is substitution x equals y plus hm of y, where the terms of hm have the order between m plus 1 and 2m. So it's only terms between m plus 1 and 2m, which transforms our system to a system in the normal form up to terms of order 2m. So this was normal form up to terms of order m, but we can transform to the normal form now up to terms of the order 2m. And then one proves that for x less, if a norm of x is less than some number smaller than rho, then the norm of this transformation fm is c some constant omega k plus m minus k. So is this omega with Bruno conditions, where m to k, c greater than 0, k kappa less than 0. And this estimation depends only on eigenvalues of m. So it means it does not depend on m. And then we see that science expression starts off terms of order m. On case step of iteration, the radius of convergence in reduces in this by multiplication by this number. But due to condition omega, you see that this number is less than infinity. So it means that radius of convergence will be greater than 0. And this iteration procedure was proposed by Victor Pliss in 1965, and who applied this to the case when a normal form is linear. So the method could be called Bruno-Pliss method. Some people call this Moser method, but paper of Moser were much later, and it's another reason. So now I would like to explain some main idea of Bruno approach. So main idea is another representation of vector fields. So traditional representation of vector field like this one. So we have x dot equals fx. So this means that we have some system of differential equation, but we also can say that this is a vector field because the function on the right-hand side, f of x, is just a vector field in Cn. Yeah? here, but Bruno in 1962 proposed to write system 6. This not in this traditional way, like a sum of homogeneous polynomials, but in this form. In this form, x dot. So it means that you take this system, but you factor out x1 from first equation, you factor out x2 from the second equation, x3 from the third equation, and so on. And then you write, take only one xq, where xq is just this one. And ni is important. Ni is here the set. It's a very important set. Is obtained in this form q, q1, qn from Zn, but only one qa, qi is allowed to be negative. Only this one is allowed to be negative. Other are greater than 0 or equal to 0. And so you take here xq, and in fact, here you have some vector in front of, if you, I goes from 1 to n, you have here a vector. And it seems that since 1964, and use following words of Bruno, most mathematicians have regarded the above notation as rather unfortunate, cumbersome, or unclear. However, the idea, in my opinion, the idea behind this notation is fundamental part of Bruno's method. And this is not just a notation. It provides a different way to represent vector fields. What I mean here? Assume you have a R2, you have a plane, real plane, and you take a point on the plane. You can represent this point on the plane using Cartesian coordinates, so you can have coordinate x1, x2, or you can represent this point using polar coordinates, so you can have polar radius and polar angle. So this is, you have the same object, a point on the plane, but you have two different ways to represent or describe this point. This, in my opinion, this is very nice analogy. So here we have a very similar situation. But in fact, this, I'm not sure that Bruno himself realized that he indeed introduced vector field. Most probably new vector field. Most probably he realized it, but he never emphasized this. And one reason is this notation is not very convenient, but we can propose a very convenient notation. But first, I recall that what is Hadamard product. We have two vectors, and Hadamard product is just you multiply piecewise coordinates. So A1 to B1, A2 with B2, AN to be spin. So I times B, Hadamard product will be such vector, yeah? Okay, I recall that Ni is this set, and N is just an union of these sets. And we call this Bruno lattice, yeah? This set N we call Bruno's lattice. Then any system of such form, traditional, we can be written also in the form, such form. So it's like Bruno's form, this one, but it's, we will see this is much more convenient. So here FQ is just vector, and xq is just this one, and you have Hadamard product. So FQ here is the same as like if you write this like if you write this as a vector, you will have this FQ. So we call such vector fields Bruno vector fields, and this vector fields clearly forms a vector space, which we denote above. They form a vector space in the sense that you can you can sum up such vector fields, and you can multiply this by a scalar function. But now we need to work with in this area of normal forms and in this area of differential equations, we all often need to work with Lie brackets. And Lie brackets of two vector fields is defined in this way. So if we have two vector fields uv from Cn, then your Lie bracket is dv is Jacobi matrix times u x minus d of u times vx. But the problem is that if you take two Bruno vector fields, the structure is not preserved by vector, but this Lie bracket. So if you have such vector field and you would like to compute Lie bracket, you can have to write this back in traditional form. Then you compute derivatives, and you obtain again traditional vector field, and you have to just rewrite this in such form. So this does not make much sense. And one possibility to overcome this difficulty is to work in the ring of invariance. So I would like to say that in fact Bruno proof of convergence is very complicated. And I discussed this proof with many very prominent mathematicians. And all people with whom I discussed, they said that they were not able to understand the proof of Bruno. Of course, I did not. I think some people who understood the proof passed away because it was given in 1970s. But of course, there are some people who understand. And one guy who understands this perfectly is Laurent Stalovich, who wrote many papers, and most important, I think, maybe this one, singular complete integrability. And in order to overcome this difficulty, he proposed to work in the ring of invariance. But of course, he understood the theory very well, and his presentation is quite logical and maybe also beautiful in some sense, but it's impossible to understand. First, he used very non-trivial homological algebra, and then he uses this language of Bourbaki. So I think nobody really understands his proof. But in this paper, we introduced Lie bracket, which preserves the structure of Bruno's vector field. And then, due to this fact, we can work very simple, in simple way with this Bruno's vector fields. So as I already have said, so what I mean by representation, one can describe the same point in Earth using Cartesian coordinate or using polar coordinates. So is one of this, I said, is traditional vector fields. Another corresponds to Bruno's vector fields. So this is traditional vector field, and this is Bruno's vector field, but they represent the same object. We thought this part under some sign is called a term. And using this Lie algebra structure of Bruno's vector field in this work with Sebastian Walker, we made some contributions to the problem of convergence of normal forms. Is presented in this preprint, but we now have we will soon upload more recent version. And in this paper, we give simple proofs of theorem of Bruno on convergence of normal form. I think it's now easy to understand. We also give drastically simpler proofs of some theorems Stalovich about simultaneous normalization of family of commuting vector fields. It's the main results of this paper. We also give some results about interrelations of convergence of normal forms and integrability of the system. And in the rest of my talk, I'm going to explain how to introduce the Lie algebra structure on Bruno's vector fields, introduce lattice of discrete vector fields, present normalizing algorithm, and explain the main ideas of Bruno's method. So recall that for any vector field, Lie bracket is defined in this way. But if we have just two terms in this lemma of this work with Tatiana Petek, if we have just two such terms, this one and this one, so here you see x is just vector x1, xn, uk is this one, v is just vector of numbers, and q is just a vector with integer coordinates, and p is vector with integer coordinates. Yeah. So in order to, so one way how to compute a Lie bracket, you can compute, rewrite this in traditional form. You can compute a Jacobi matrix. You can compute what you will have here, and then you will have something. But then you will have to rewrite this in then in Bruno's vector form. But we have very simple formula that Lie bracket is just computed in this way. So if you have two terms, then this will be your Lie bracket. And here it's very simple. You just sum up two vectors, and this is a vector of numbers, and this vector of numbers is computed using this very simple formula. So it means here we have p, q, this vector of integers. This is a given vector. You just compute inner product, and here you compute another vector product. You number, this multiply this number by vp with vp, multiply this number with uq, and subtract. And you have a Lie bracket of two such vector fields. But of course, when we work with vector fields, we always need some grading. So with this operator, Bruno vector fields becomes Lie algebra, which we denote by M. So vector space is denoted by F. Lie algebra is denoted by M. And we need to grade them. So we grade this, we grade M using Zn, and we define a homogeneous component of mu q of our Lie algebra in this way. So homogeneous, the space of homogeneous polynomials of degree q is just 0 if q not from here. O is this of this form. So this is every homogeneous polynomial of degree q looks in this way. And you see that we have this grading equality. So it means that from this equality we see that we have graded Lie algebra. And now this q is called degree. So degree now is not a number, but degree is a vector. Yeah, degree is a vector, so it's a big difference. Usually by degree of polynomial or vector field you mean some number, but here degree is a vector. So this q is degree of this term. So for q not equal 0, this term is called resonant if you have this condition. Notice that usually in traditional theory of normal form, this is a resonant condition. But in Bruno's theory, this is a resonant condition. And this is traditional resonant condition. And now assume that Zn is ordered using a lexicographic term order with x1, x2 greater than 1, and vector field written according to this order. And with this order, M is now a gradient Lie algebra, which we denoted by Blex. And we say that the vector field, this vector field of from this Lie algebra is in the normal form up to degree p. So p again is a vector. If for all q less than p, fq equals 0 if q is not necessary. So normal form contains all the resonant terms. All non-resonant terms are killed. And now assume that the matrix A is diagonal with the eigenvalues lambda 1, lambda n, and lambda is lambda 1, lambda n transpose. And we have theorem, which is actually provides the simplest algorithm to compute Poincare Dulac normal form. So assume that vector field, our vector field, is in the normal form up to degree q. Now let S be greater than q, fs not equal to 0, and there is no t such that between q and c, so between q of t, all these coefficients of t are equal to 0. So then if we have this condition, then it means that S is a resonant term, and our system is in fact in the normal form up to degree S. But if is not equal to 0, that it means that we have non-resonant term. We have to delete this non-resonant term. And then we just compute vector field H of x in this way. And now H of x now is exponent of x. Then performing the substitution, and changing y to x, we obtain from our vector field the vector field in the same form, but now it's the normal form up to degree S. So in fact, this substitution is just needed to recompute the right-hand side of our system. And how it works, algorithm works. So let's take Q. Recall that Q is absolute value Q is computed in this way, where Q1 just coordinates of vector Q. And we are given such polynomial vector field, and we would like to compute the normal form of this vector field. So this is given, A of x is given. A is diagonal, but it's not necessary. We have our algorithm, in fact, works for Jordan form. It can be in a Jordan normal form, not necessarily diagonal. But for simplicity, I assume that it's diagonal. So, and we have, we just write Q1, Q2 according to lexicographic order. According to lexicographic order, and we do normalization step by step for every Q, So for I from 1 to M, if the term is non-resonant, then you just compute H. Then you recompute the right-hand side. So instead of this, using adjoint operator, which is computed, generated by this H, we just recompute right-hand side. Then you denote this B as AX, and you repeat the procedure until you kill all non-resonant terms here. So this is really simple. But let's see what is in fact important here. Important is the fact that these Bruno vectors fields are in fact discrete, or maybe I don't know actually how to better to call this discrete of lattice vector field. We call them lattice vector field. And I will try to explain what is here we have. So Ni is this set, N is this set. Now P is a vector with integer coordinates. F and G are vectors from Cn. And we can define, we can write a pair, F and P, and we define multiplication in this way and addition in this way. So F is a vector from Cn, G is vector from Cn, but P is vector with integer coefficients. And then we can define summation and multiplication by constants. So it is convenient, but we can, instead of such notation, it's better to use such notation, F sub index P, G sub index Q. And it's convenient to think about this Fp as a vector F assigned to element P of Bruno's lattice. Yeah, I will draw a picture later on. And now we let any n be the set of all formal series of such form. So it's just some discrete objects. But we have isomorphism. We have isomorphism which works this way. We denote it as T. So if we have Bruno vector fields in this form, then we just set x equal to 1. And then from Bruno vector fields, you have this our discrete series of this form. And this is an. First, it's a vector field isomorphic to the space of vector space of Bruno vector field, but it's also Lie algebra. Lie algebra is isomorphic to M. And because it is possible to see that we can just define this Lie bracket in this way, and it will work. It's this Lie bracket, yeah. So we have isomorphism. And I would like to, we can do some visualization of this. So it's our vector field. And now this in this way we have compute Lie bracket, but what is now traditional vector field and what is Bruno field up to this isomorphism. Up to this isomorphism, when we have a vector field, it's linear vector field, yeah? You just can take, you can take vector. So to each point is attached a vector. But if you write this in Bruno's vector form, that you have, instead of this form, you write x dot y dot equals xy times 1 over 2, x0 was 0, so it means q is 0, 0, fq is 1, 1/2. So it means you can draw this vector field using just such arrow, yeah. This is, and if you have, because we have only one arrow, but because we have many arrows, then it goes in this way. You can go this way. And we can do normalization algorithm using this discrete structure and how it works. So you can write this in discrete in Bruno's form. Then to each you can visualize in this way. So this is a vector field, but to each point of a lattice is attached a subvector. Then normalization procedure. If you just look on the picture, normal forms corresponds to line q lambda equals 0. In this case, it's just this line. So it's your original vector field, but then you do normalization, it means that you get rid of vectors which are not on the line, but maybe on the line will appear some other vector. So first you get rid of this vector, what disappears this one and this one. Then you get rid of this vector, you have this picture, and then you get rid of this vector and you have this picture, and you have your system in the normal form. I think maybe I do not have to explain the details of the Bruno-Bliss method, but I just would like to explain some to mention a few things. So when one question is when a Ziegler-Bliss condition holds, when condition omega is satisfied. So first statement, if the Ziegler-Bliss condition holds, then condition omega is satisfied. It's easy to prove. But if all lambda I are algebraic numbers, then a Ziegler-Bliss condition holds, and therefore we have condition omega. So this is quite important theorem, and I think it's quite a trivial theorem for people who works in number theory, but maybe they know something like this statement. But we, for people working in differential equations, very important statement, and I believe people working in differential equations do not know that this is true. So it's one of our results also in this paper. Here is a proof. And maybe I go to conclusion. So I can say that simplified condition A is the existence of the same number of independent analytic first integrals of the number of monomial first integrals. And by result of Jean-Libre, Pantazzi, and Volcker, the existence of n-1 analytic local first integrals is a n-dimensional system is simplified conditions A. But we obtained some generalization in this our paper. And maybe relation to CAM theory. The CAM theory is about single complete integrable Hamiltonian system, and another terminology is partial integrable systems. But it appears that the theory of Bruno with extension of Stalovich presented in these papers covers almost at least many aspects of the Ham theory. And I think it's a deeper investigation of the relationship between single complete integrability and the CAM theory appears to be a promised direction for future research in this direction. Okay, so that's all. Thank you for your attention.